Hello everyone, welcome back to the NPTEL course on materials informatics, and in this lecture we will continue our discussion on density function theory from the last lecture. So just as a recap of what we discussed in the last lecture, we looked at Hohenberg-Kohn theorems as the mathematical formulations of your density function theory. This along with variational principle and Born-Oppenheimer approximation and Pauli's exclusion principle basically power your modern day DFT calculations, right. And we also looked at exchange correlation functionals as a key approximation to density function theory, and since this is mathematically unknown, there are a whole zoo of them, and we looked at two different approximations. One is the local density approximation or LDA, the other is the generalized gradient approximation or GGA, right. And in this lecture we will continue our discussion on exchange correlation functionals, and we will also look at some of the other approximations and other sort of rules of thumb to keep in mind when we do typical density function theory based calculations. Okay. So in GGA we introduce some amount of non-locality in the exchange correlational functional by taking into account both the gradient as well as the electron density at a given point in space, right. So in meta GGA we basically try to include even more non-locality, right. So the idea is that if you take into account more and more information about how the electron density can vary, right, across a wide region of space, you basically can approximate how the electron density is varying at a given point in space. So electron density at a given point in space may depend on how the density itself is varying across a wider region of space, right. So the more non-local information, the more wide information that you actually take into account in the construction of your exchange correlation functional, the more accurate you can be in terms of describing your electron density itself. So that is basically the idea behind your meta GGA. So they take into account more non-local information than what is taken into account in typical GGA. So how do you do that, right? So you basically either take what is referred to as kinetic energy density or the Laplacian, the second derivative of your electron density itself, right. So LDA took just the electron density, GGA took the gradient of the electron density, the first derivative, and meta GGA is typically take an equivalent of the second derivative, right, of the electron density. So you can either take a straightforward second derivative, which is just a Laplacian. So you take del square of n, right, and you incorporate that information in your meta GGA. The other way to include this non-local information is to take the kinetic energy density, right. So kinetic energy densities are basically Laplacians of your one electron wave functions, right. So one electron wave functions are in turn related to your electron density. So it is basically the integral of all one electron wave functions over all all of space, right. So that is basically your electron density. So if you take kinetic energy density, you are somehow including the second derivative or the curvature effects of your electron density itself, right. So you can take in either kinetic energy density or the Laplacian of the electron density. So both approaches are possible in meta GGA. The kinetic energy density sort of comes from a historical development of exchange correlational functionals also, right, how LDA was formulated and so on. So there is some physical and mathematical background to which there is a preference to using kinetic energy density instead of just taking in the Laplacian, but both approaches are equally possible, right. In terms of the state of the art in meta GGA functionals, I would say the state of the art is the strongly constrained and appropriately normed or SCAN functional. So this was developed in 2015. And the nice thing about SCAN is that it satisfies all the 17 known constraints for exchange correlation functionals, right. So when you formulate an exchange correlation functional, you cannot use any arbitrary mathematical function. You have to ensure that they satisfy some kind of norms, bounds, and they also reproduce the behavior in some well known or well characterized systems, right. So that this reduces the arbitrary nature of coming up with functionals for the exchange correlation behavior. In terms of developing these exchange correlation functionals, so far we sort of know there are about 17 constraints that a functional has to satisfy, and SCAN sort of satisfies all 17 of them. So in contrast, PBE, which is one version of GGA, so the Perdue-Bokeh-Earnshaw functional satisfies about 11 constraints if I am not wrong out of the 17. But SCAN satisfies all the 17 of them, which makes it theoretically more accurate than all of the other sort of LDA GGA or other meta GGA functionals that are available. So it's theoretically guaranteed to be accurate, and it is also gaining in popularity. There are some convergence difficulties with SCAN, so the computational cost is sort of slightly higher compared to if you do simple LDA or GGA calculations. Right, and sort of benchmarking studies over the past decade have shown that SCAN does improve upon GGA. So it does improve the description of weak bonding, so van der Waals interactions, hydrogen bonding much better compared to that of GGA. The correlated systems, so transition metal oxides, transition metal halides and so on, are also treated better than GGA, but there are still problems. So not all systems are treated better. There are few systems that are treated better, few systems where problems persist. The band gap problem, so underestimation of band gaps, is actually lower than GGA, but again the problems are there. So SCAN also underestimates band gaps compared to experiments, but it underestimates them less frequently compared to GGA. And the computational cost definitely is higher than GGA, so there are some convergence difficulties associated with doing SCAN calculations compared to that of GGA. So after SCAN was developed, there have also been modifications done to SCAN to improve this aspect, to improve convergence difficulties and reduce computational costs, and they are referred to as RSCAN and R2 SCAN. So restored SCAN, restored regularized SCAN and so on, and those functionals are also sort of equally popular compared to SCAN, but they do not satisfy all the 17 known constraints, so they actually have to break some of the known constraints to ensure that the convergence difficulties are fewer and computational cost is lower, right. So SCAN till date remains the only meta GGA functional that satisfies all the 17 known constraints for exchange correlation functionals. So how does SCAN do with respect to predictions? So this plot here shows the energy differences between DFT and experiments with different functionals here, and also how the coordination number actually changes, right. So this is coordination number of a given ion predicted with DFT, and this is coordination number basically predicted with experiments. We see that in general, so PBA has a tendency to both under coordinate to a larger extent compared to over coordinate systems. If you add what are referred to as dispersion corrections, so to account for the fact that PBA does not get all the weak bonding interactions very well, you can add additional corrective terms to your exchange correlation functional, and if you do that, the problem becomes lower in under coordination, but it sort of shifts to over coordination, and we see that in the case of SCAN the problem is less severe. So you are sort of more on the exact line here compared to that of PBE, and same with SCAN if you add an additional dispersion corrections. So you add an additional terms to account for weaker bonding interactions. There are more data points on the exact line compared to the corresponding version of GGA. Right. So in general, in terms of structural predictions, we see that SCAN is better than PBE, and even if you add dispersion corrections to account for weak bonding interactions, SCAN is still better than that of PBE, right. And the other sort of important problem that PBE has, so PBE in general tends to underbind systems, right, but one notable system that it actually overbinds. So its bond length of the system is actually lower than experiments, and the cohesive energy or the binding energy is way higher than experiments, is actually oxygen gas. So PBE is known for overbinding oxygen gas, and this sort of introduces systematic errors when it comes to oxidation energies as well as formation energy predictions. So prediction of different thermodynamic properties, and we see that SCAN does not have this problem. So this is a plot of calculated calculated or predicted formation formation enthalpies versus experimental formation enthalpies of various oxides, right. So you have calcium oxide, magnesium oxide here, you have silica here and so on, so various types of oxides here, and we see that SCAN basically predicts all the formation energies along this line, along the parity line, right. So SCAN does a very good job of not overbinding oxygen gas, which PBE does, right. So SCAN is in general good for structural predictions, and for thermodynamic predictions also SCAN is better compared to that of PBE, right. So I was referring to the fact that LDA, GGA and SCAN all have problems with correlated systems. So systems like transition metal oxides where you have strong interactions between your d electrons right across the transition metal centers. And the problems associated with correlated systems can be traced to what is referred to as self interaction here. Right. So let me explain what self interaction is, and this self interaction is observed is an issue with all density function theory based exchange correlation functionals. So be it LDA, be it GGA or be it meta GGA, all of these functionals have some amount of self interaction errors. Right. So what is self interaction, right? So in DFT we represent your electron densities as the summation or integral of your one electron wave functions, right? So you use this electron density as the variable, right? Now if you think about how electron density itself is interacting right with itself, so or in other words, how do we actually evaluate this Hartree term, which is the electron repulsion term. So what we do it in practice is we are writing this as a functional of our electron density here. So we do a simple multiplication of the electron density. So this is equivalent to charge at position of R1 and charge at position of R2 here, right. So that's what we are basically doing. We are multiplying the electron density at a position R1 with the same electron density variable at a different position R2, and then we take the differences between the two positions R2 and R1, and if we evaluate over all space, we basically get our electron repulsion term, right. So you see that in evaluating this electron repulsion term, your density is interacting with itself, right. So these two are the same variables, just they are physically separated, right, which implies densities are interacting with themselves, and density at a given point can come because of electrons at R1 but also because of electrons at R2, right. Same thing with the other way around here. So the density at R2 can come from electrons at R1 as well as electrons at R2, right. So which implies since you are just multiplying density with density, your electrons that are contributing to the densities can end up interacting with themselves, right. So if you have a scenario where you have an electron that is delocalized between these two positions, between R1 and R2. So a given electron exists both at R1 and at R2, and if you are evaluating this electron repulsion term, right, you are not accounting for the fact that it's the same electron that contributes to the density here and the density here, right. In other words, the same electron is repelling with itself, right. And this is something that is artificial, right, because if we are actually modeling all the individual electrons by their own by the many body wave function, right, where all the electrons see all the other electrons, then these kind of self interactions would not arise, because you can precisely identify the wave function associated with one electron, and then you can only calculate repulsions with respect to wave functions identifying the other electrons, right. So since we are using a common density variable here, we end up including interactions of electrons with themselves, which is artificial in nature, and hence this repulsion is also artificial, right. So this electron repulsion terms that arises from electrons interacting with themselves is an artificial repulsion term, right. This is not what should exist in a real system, right. And because of this artificial repulsion, and because you always try to minimize your energy, or you are trying to reduce this electron repulsion, we will see that if you do this in a self consistent fashion, right, if you do a calculation in a self consistent fashion including this electron repulsion term, it causes spurious delocalization, right. So the electron is repelling with itself, right, and the electron wants to reduce the repulsion with itself, which implies it will try to increase the distance that it is spreading over, right. So it will try to increase the distance between R2 and R1, or the electron will sort of delocalize or stretch itself, right. So so this causes spurious delocalization of electrons, right. So electrons, because of repelling with themselves, they are forced to occupy a larger amount of space or delocalize compared to what they should be doing, right, what they should be doing in reality. And this problem of electronic delocalization is particularly severe in transition metals and F block elements, right. So in transition metal and F block elements, when they form compounds, so when they form oxides, fluorides, chlorides and so on, their d and f orbitals become quite contracted, So if you take iron oxide for example, like Fe2O3, in Fe2O3 each iron ion is has an oxidation state of 3 plus, right, and because of this because of this oxidation state, right, so each ion has 3 more protons compared to the electrons, right, compared to the net amount of electrons, because it has donated 3 electrons to a nearby oxygen, right. So because of this, because of the higher nuclear charge on the iron atom, the orbitals tend to contract, right. So the d orbitals will occupy a smaller amount of space than they should or than they would if iron was in its metallic state or an oxidation state of 0, right. So the orbitals become contracted when the transition metals form bonds or donate electrons to oxygen ions, to fluorine ions, chlorine ions and so on. And because of this contracted nature of d orbitals, you now need electrons to occupy smaller regions of space, right. So you want your d electrons to occupy these d orbitals, right. So iron 3 plus still has 5 d electrons. So iron has an atomic number of 26, so its valence electronic configuration is 6 d electrons and 2 s electrons. When it forms an iron 3 plus ion, it is going to donate the 2 s electrons and one of the d electrons. So it still has 5 d electrons which are going to occupy the 5 different d orbitals. But the d orbitals are smaller, which implies electrons in reality will occupy smaller regions of space amongst the different d orbitals. But because of this spurious electron-electron repulsion term, electrons will now delocalize and they will not occupy the smaller regions of space representing your d and f orbitals. And if they are not occupying the correct orbitals, then you basically have an incorrect representation of your ground state, right. And that is the problem of using regular density function theory calculations for representing transition metal or F block based compounds, right. So such as iron oxide, nickel oxides and so on. For F block elements you can think of ceria, even lanthanum based oxides or gadolinium based oxides and so on, right, oxides, phosphates and so on. So if we are modeling F block elements also, this can be a particularly severe problem, right. So this artificial repulsion of electrons with themselves is what is referred to as self interaction, right. And since this is artificial in nature, right, so electrons are interacting with themselves, repelling themselves, so that is referred to as self interaction. And since this is artificial, this is not what is observed in real systems, this is referred to as a self interaction error or SIE, right. And if you are actually using Hartree-Fock, so Hartree-Fock which uses sort of slated determinants to represent the many body wave function, Hartree-Fock does not have the self interaction problem per se, because it has a perfect cancellation of terms. So there is perfect cancellation between the Coulomb terms that arises from self interaction and the exchange term that arises from self interaction, and because those two terms sort of cancel themselves, Hartree-Fock does not have this problem of self interaction. But any functional, any exchange correlation functional in the framework of density function theory will have some level of self interaction error or self interaction problem, okay. Okay, and this self interaction error or self interaction problem also leads to the lack of derivative discontinuity in a given system. So what I mean by derivative discontinuity, right? So let us say we are tracking the total energy of a given system as a function of number of electrons. So I am either removing electrons, so I can ionize electrons here, or I can add an electron, so to measure electron affinities of my system, right. So any system is guaranteed to have only an integral number of electrons. So electrons are quantum particles, so I cannot remove a fraction of them. I have to either remove an electron in its entirety or add an electron in its entirety, right. So which implies if I just calculate the energy, right, the energy should be sort of discrete, right. So it should have certain energy at n electrons, certain energy at n minus 1 electron and certain energy at n plus 1 electron, and between these two there is no real definition of an energy. So because these systems are not physical, so which implies if you want to calculate energy of a system that has half of it has n electrons and half of it has n plus 1 electrons, for example, you take a weighted average of the system with the fraction of system that has n electrons and fraction of system that has n plus 1 electrons, right. So you'll only take a weighted average between this n electron energy and n plus 1 electron energy. So any number of electrons that is between n and n plus 1, you will sort of represent the energy as a straight line. So the straight line basically represents a weighted average, right. So this is how your actual system should behave. So n minus 1 has a distinct energy, n has a distinct energy, and n plus 1 has a distinct energy. So energies between them should always be a weighted average. So you will have piecewise linear interpolation across these data points, right. So since you have piecewise interpolation, you see that if you now take a derivative of the total energy with respect to number of electrons, right. So you take a derivative of this function, at each integral point you have a discontinuity, right, in your derivative, right. So here the derivative is well defined, here the derivative is well defined, but at this point you have two different derivatives, right, two different derivatives that are possible, or in other words your derivative itself is not continuous. So it has one value here and then it has another value here, right. So one value in this negative limit approaching n, another value in this positive limit approaching n, right. So the derivative itself is discontinuous, and this is how exact systems, right, or actual physical systems should behave. This is how systems should behave. But if you use any local or non-local functional, local or semi-local exchange correlation functional such as LDA, since your functional form is all continuous here, so LDA is not built in to have any discontinuity with respect to number of electrons, you will see a smooth variation of energy with respect to number of electrons. In other words, if you use a local or semi-local functional, that functional does not have the derivative discontinuity that real systems should have, right. So this does not have, and we can also think about why this why there is a lack of this this sort of derivative discontinuity in actual functionals. So we can sort of attribute this to a combination of two errors here. So one is because of the delocalization itself, right. So in LDA or GGA or even meta GGAs to some extent, your electrons do delocalize compared to what they should be. And the resultant self interaction error, right. So the delocalization can cause sort of larger slopes in some regions and then smaller, and the resultant self interaction error can cause lower slope in other regions, right. So if you use a local or semi-local functional, you do not get back the derivative discontinuity, which leads to predominantly inaccurate band gaps and inaccurate electronic structure, right. So in normal materials, right, so the band gap is basically the band gap or the fundamental gap is basically related to the energy difference between your ionization energy or the energy required to remove an electron from a system and the electron affinity, which is the energy gain that you get when you add an electron to the system. So the idea is that when you remove an electron, the electron comes from the valence band maximum in a given system, and when you add it back, right, when you add an additional electron to the system, it goes into the conduction band minimum. So basically the difference between the two terms gives you your band gap, gives you your fundamental band gap in your system, and if your exchange correlation functional does not recover this derivative discontinuity, it is going to be inaccurate in the prediction of your band gap, right. And this also leads to consequences in the prediction of the electronic structure itself. So in cases where your let us say your semiconductor, you have a semiconductor which is indirect in its band gap, your exchange correlation functional may predict that to have a direct band gap and vice versa, right. So such inaccuracies sort of creep in because of self interaction error, which leads to a lack of derivative discontinuity in our exchange correlation functionals. So one way to fix or mitigate, reduce this self interaction error is to mix a portion of what is referred to as exact exchange or Hartree-Fock exchange to density functional theory. So Hartree-Fock does not have the self interaction error because of perfect cancellation between your Coulomb and exchange terms, right. So it actually recovers back your recovers to a large extent this discontinuity in the derivatives of energy with respect to number of electrons, right. And the way to also interpret why Hartree-Fock exchange or exact exchange does not suffer from this derivative discontinuity is because it includes more non-local information than what is included in your local or semi-local functionals in your LDA, GGA or meta GGA functionals, right. The way we sort of can include Hartree-Fock interactions or exact exchange into DFT is to basically calculate this exact exchange term through Kohn-Sham orbitals and then add it to our exchange correlation functional. This is not exact though, because Kohn-Sham orbitals do not represent actual 1 electron orbitals, but this is a fairly good enough approximation. And we can see, we sort of see it in practice that including exact exchange does reduce the amount of self interaction errors that you have and mitigates the derivative discontinuity problem or lack of derivative discontinuity that you have in your semi-local functionals. So this has also been shown. I mean, this is a simple calculation in a Beryllium system. You see that if you use LDA, you still get a fairly smooth function. The dotted lines basically tell you how the discontinuity should look like. So they basically illustrate straight lines. You see that LDA is sort of still smooth, but then if you include any amount of exact exchange, you recover back your derivative discontinuity. Or in other words, your data points all lie more on the straight line than in the case of LDA, right. So if you mix a portion of exact exchange to DFT and the resultant functional is what is referred to as a hybrid functional. So hybrid functional has in its exchange correlation term some portion of exact exchange as well. So some portion of Hartree-Fock exchange. A couple of popular hybrid functionals are HSE06. This is quite popular among material scientists or physicists who are more interested in solid systems, and B3lib, which is more popular among chemists who are interested in more molecular systems, right. Hybrid functionals do fix some of the problems of non-local functionals. They do give you better band gaps compared to what you get in LDA GGA or meta GGA functionals, but hybrids do not fix all of the problems. They do get wrong ground states and they do have underbinding problems of bonds. So they do overestimate the bond lengths compared to what they should be. And the main problem with most of the hybrid functions is that they result in a significant increase in computational costs, right, because your Hartree-Fock exchange or Hartree-Fock calculations do not scale computationally cubically, right. So they have n to the power 5 or n to the power 7 scaling, whereas regular DFT has n cube scaling, right. So they do not scale cubically, which implies your computational cost, even if you only include some portion of this Hartree-Fock exchange, of this exact exchange in your calculation, your computational cost is going to increase significantly, right. So hybrid functionals fix some of the problems, but not all. So they do give you better band gaps, but they can result in worse thermodynamics. They can result in bad geometries, so underbinding of bonds and so on, and they result in a significant computational cost. Okay, so just as I reiterated in my last slide, so hybrid functions, specifically the HSE06 functional, does lead to better band gap predictions compared to your semi-local functionals, your LDA, PB functionals and so on, and that's illustrated in this plot here. So this is the computed band gap versus the experiments. You see that most of the semi-local DFT functionals such as LDA, GGA and so on, they all underestimate the band gap, whereas hybrid functionals HSE sort of is more closer to the parity line. So it sort of predicts band gaps very close to the actual experimental values. Okay. Another way to sort of reduce this self interaction error and the resultant derivative discontinuity problem is to introduce an additional correction term called the Hubbard-U correction. Right. So what does the Hubbard-U correction do? So the U parameter is typically added as an energy penalty term. So it adds a penalty to your Hamiltonian. So to your Kohn-Sham Hamiltonian, it adds a penalty term for delocalizing electrons. So basically, if your resultant charge density that you get from your self-consistent calculation is more delocalized, right, than it should be, then it causes an increase in the overall energy of the system. Right, and in density function theory based calculations, we always try to reduce the overall energy because we want to approach the true ground state energy. So since this is an energy penalty term, the self-consistent field calculation automatically tries to reduce the electronic delocalization as much as possible and puts electrons in designated orbitals, in designated d orbitals, for example, right. So U is added as an energy penalty term, and the U itself is a multiplicative term to sort of occupancies of orbitals, and this U term can also be specific to different orbitals. So it's more commonly added as an energy penalty term for contracted d and f orbitals, right. So that's where it's more commonly used. In some occasions the U has also been used on p orbitals of oxides and so on. So basically it's added as a penalty term, and it's commonly added to d or f orbitals. Adding U does reduce errors of your semi-local functionals, so LDA, GGA and SCAN. It does lead to better ground state polymorphs, leads to better magnetic states, also gives rise to reaction energies, and it is computationally as fast. So it does not increase the computational complexity compared to hybrid functionals. It is the same computational cost as your semi-local functionals, but there are some drawbacks as well. So the value of U itself is not known a priori. So this U is an energy penalty term, right. So how much penalty you give for delocalizing electrons actually depends on the transition metal itself. It depends on the orbital. It depends on how you are representing your wave functions. It can also depend on even on the oxidation state of your transition metal in a given system, right. So the value of U is not known a priori, which means we have to find a way to get that U value. In metals, with metals DFT plus U is extremely bad news, because in metals you have delocalized electronic states, that is the ground state configuration, but adding a U term will always force the delocalized electrons to localize, right, which implies in metals you are guaranteed to get a wrong electronic structure if you use DFT plus U, right. So DFT plus U is bad news for metals, and if you use different U values for different compounds of the same transition metal, right. So for example, let us say in FeO and Fe2O3, so FeO has iron in its +2 oxidation state, Fe2O3 has iron in its +3 oxidation state, and if you use two different U values for the two different oxidation states, then you cannot compare the energies of those two compositions in a straightforward fashion. So let us say you want to calculate the energy for a reaction, FeO oxidizing to form Fe2O3. If you use one U value for FeO, another different U value for Fe2O3, then there is no straightforward way for you to calculate the energy of that reaction, energy of that oxidation reaction. So mixing energies with different U values is not physical, because if you modify the U value, basically you are getting a different Hamiltonian, right, for which you are solving for the energy. So you cannot straightforwardly compare two different Hamiltonians within the DFT framework, right. So mixing energies with different U values is not physical. So there are some drawbacks with adding in a U value, but it is a computationally easy approximation to include this U value. So just to visualize, right, how this U value sort of corrects for this this derivative discontinuity. So let us say you have a semi-local functional that sort of has an error with respect to the actual straight line here. So the actual linear or piecewise interpolation here. So let us say you have your semi-local function is underestimating here. You can sort of imagine the U to add a positive correction term. So since it adds a positive correction term, you see that this blue curve will start shifting closer towards the straight line here. So that is how the U correction is mitigating or reducing the self interaction error. And if you if you manage to add the appropriate amount of U correction, it can lead to better ground states and better magnetic configurations as well. So I am showing a couple of examples here. So one in the case of Ceria, so this has f orbitals. So in the case of Ce2O3, right, so you have two different polymorphs. So one is the hexagonal polymorph, other is the cubic polymorph. You see that in both the polymorphs, so in the hexagonal as well as in the cubic polymorph, if you just use the scan functional, it predicts both of them to be metallic in nature. But if you add appropriate U correction, you see that the actual semiconducting nature of both hexagonal and cubic polymorphs is recovered. So both polymorphs are actually semiconducting in nature, and if you add the appropriate U correction, you actually recover that semiconducting nature compared to pure scan functional, and this actually leads to the correct prediction of the ground state. So Ce2O3 in its ground state is actually hexagonal in nature, and you actually recover that correct ground state if you add the appropriate U correction compared to if you do not add the U correction, right. And this we also see in the case of manganese oxide. So you recover back the right ground state of both ferromagnetic and antiferromagnetic states in Mn2O3. So if you add the plus U correction, you once again see without plus U, if you just use plain scan calculation, both the ferromagnetic and antiferromagnetic configurations are treated to be metallic, but if you add the right amount of plus U correction, you see that you recover back the semiconducting nature of both the ferromagnetic and antiferromagnetic configurations of Mn2O3. Right. So this is an example of a d orbital system. So Mn2O3 has valence shell filled with d electrons. We see that the U correction plays a crucial role, right. So adding U basically gives you better ground states and better magnetic configurations as well in both in both your rare earth systems such as ceria, and also transition metal oxides such as manganese oxides. Okay, so just to give some general advice, right. So let us say you are new to doing DFT calculations. Where do you start with? What kind of exchange correlation functional do you choose? In general, PBE is a good place to start for most solids, right. So almost always your first DFT calculation should be with PBE, and then you can increase or decrease the complexity depending on the problem of interest, right. So PBE is almost always a good place to start, but let us say you are after good structures. So let us say you want right geometries, right bond lengths, if you have an oxide or if you have good computational power, almost always you should use scan to begin with. So if you want good structures, use scan. If you have an oxide, try to use scan, and if you have good computational power, definitely start with scan. If you have correlated systems, so if you have transition metal oxides, transition metal halides, rare earth oxides, rare earth halides and so on, try to use the Hubbard-U corrected version of either PBE or scan as a start. You can go for hybrid functionals later, but definitely you can try with the Hubbard-U corrected functionals as a start because they are computationally cheaper. The U value, of course, you may not know a priori, so take it from reliable literature. There has been a lot of literature which has devoted itself to finding good U corrections for both PBE functionals as well as scan functionals. So take U from a reliable literature. But if you are after electronic structure, so let us say you want good band gaps and good electronic structure, and if your underlying system is a semiconductor or insulator, use a hybrid functional such as HSC06. If you have a metal, then use PBE. PBE is the best functional for metals. Okay. Some additional things to note, additional approximations or corrections to note. So systems that have weak bonding interactions or what are referred to as dispersion interactions, generally you can have some functionals that add that correct for your exchange correlation functional not capturing this dispersion interactions very well. And these exchange correlation functionals are referred to as dispersion corrections. So there are corrections that account for van der Waals interactions, so they help your functional to model these van der Waals interactions very well. These are usually semi-empirical in nature, and whatever corrections you use, they are usually dependent on the choice of functional itself. So each functional will have its own suite of dispersion corrections that are available to them. So use them carefully. So read some literature and then see what people have used and then use them carefully. If you have to use spin orbit coupling, then you have to again take into account additional interactive terms in your exchange correlation functional. So these require typically sort of more complicated calculations. So once again sort of read the literature carefully on how to account for spin orbit coupling and then include those coupling interactions well. And these coupling interactions are important in heavy metals such as bismuth, lead and so on. These spin orbit couplings can play a big role in determining the underlying electronic structure. In certain oxides and compounds of transition metals as well as rare earths, you can get these very nice non-collinear magnetic states, and non-collinear magnetic calculations also require some modifications to be made in how the spin interactions are actually modeled. So these are again more sort of heavy calculations. My advice would be to again read up some literature if your system is non-collinear in nature, and then do non-collinear calculations. You can also go beyond DFT in terms of calculations if the properties of interest are in that state. So if you want more sort of exact band gaps, for example, fundamental gaps, you would probably need to do some amount of GW calculations. If you are interested in electronic transport, excitons and so on, then you may need to solve this Bethe-Salpeter equation also. If you are interested in how electronic states are evolving with time, then you may have to do time dependent DFT calculations. And if you are interested more in the exact solution, if you want to get as close to an exact treatment as possible, then you could consider random phase approximation. But these are all of these calculations are generally very expensive computationally, but they can yield very good, very accurate electronic and optical properties. So if you have to use them with care, because these can be quite expensive computationally. So these are just additional set of calculations or approximations that to keep in mind if you are interested in systems that have dispersion corrections, that have spin orbit coupling, or if you are interested in properties that are beyond the DFT scale. Okay. So we will take a recap and then stop with this lecture. So we looked at DFT. One of the key approximations of DFT is the exchange correlation functional, and there are a whole zoo of them. We looked at LDA, GGA in the previous lecture. In this lecture we looked at MEDA GGA hybrid and DFT plus U approximations, and all of these functionals have their own strengths and weaknesses. So in order to evaluate their strengths and weaknesses, always try to see whether these functionals are overbinding or underbinding your systems, what is the extent of self interaction errors they have in your system and the resultant derivative discontinuity, and how much computational expense these functionals are going to incur for you, right. So we are not done with DFT yet, so we will continue our discussions on DFT towards more practical aspects of doing a DFT calculation in the next lecture. So with that, I thank you all for joining this lecture on DFT, and I will see you all in the next one.